ওয়ালাইকুম আসসালাম, শোনা যায়? ওয়ালাইকুম আসসালাম, প্রপারলি শোনা যাচ্ছে? ওকে। না, ইউ আর নট লেট। ঠিক আছে, আমরা এখনই স্টার্ট করতেছি। জাস্ট স্টার্টিং রাইট নাও। ওকে, ক্রিস্টাল ক্লিয়ার। ওয়ালাইকুম আসসালাম, স্টার্ট করব। শুড বি স্টার্ট নাও? Yes sir, we should. Let me call the home is. স্যার, ক্লাসের শর্টে একটা রিক্যাপ দেন। Yes, I'll give a short recap. Okay. Okay, let me start. None of you have joined. So we start off with where we left off with the reading material, right? So last class we studied a couple of things, and I will summarize that and recap it a little bit. So we are studying cosmology, right? So we are studying cosmology, that is the last topic in your astrophysics unit. So in the early 20th century, like we said, astrophysicists discovered that the galaxies in our universe are what? All moving away from each other, right? All of them, all the galaxies in our universe are moving away from each other. And they're all moving away from each other at great speed. Okay. So all the galaxies in our universe are moving away from each other, and they're moving away really quickly, very fast. So the galaxies are moving away from each other, so the universe is expanding, and the expansion rate is very fast. It is very fast. So this is due to the fact, why is this is due to the fact that the space in our universe is expanding. So it's not like the galaxies are moving away from each other, it's rather the space between the galaxies is expanding. Okay. So, and then we talked about some evidence that we will study today, and we talked about the Big Bang theory briefly. We will study it in details today. And we also said that the Big Bang Theory predicts that the universe was formed 13.8 billion years ago. We will talk about what we know about this and what we don't know. I will try to brief it. Okay, so now background information. Since 17th century, cosmologists had struggled with the problem. What was the problem? Do you guys remember? There was a problem in physics world in 17th century. Well, Newton comes up with the law of gravity, and the law of gravity makes sense for all objects. Fine, law of gravity makes sense for all the observations that we make. But also one thing that doesn't make sense is a universe governed by gravity alone would naturally collapse at a faster and faster rate, right? Because gravity attracts. So if everything attracts each other, then all galaxies should collapse into one single point because they will all attract each other. However, that is not the case. We know that that is not the case because if we look up at the sky, empty at the night sky, the universe seems to be mostly empty space. So this is paradoxical. Like, what are you trying to say? That we are that then that if the universe is only governed by gravity, then it will collapse at a faster and faster rate. But in reality, most of the universe is empty space. That means the universe is definitely not governed by gravity alone. That's one thing we are sure. The universe is not governed by gravity alone. There are other forces as at play in empty space. The answer to this riddle came in 1929 when Edwin Hubble. Do you guys remember what Hubble discovered? Hubble discovered that Hubble mainly observed very distant galaxies. So galaxies that were well outside of our local group. Hubble mainly observed those galaxies that are well outside our local group. So those are very distant galaxies. And by splitting their light into spectrum, do you remember how we split light into its spectrum? Can anyone guess in the comments? How do we split light in the how do we split light into its spectrum? Prisms. That's right, prisms. So we use prisms to split white light into its all of its different colors and its different wavelengths. That is splitting it into its spectrum. Alright, and he found that its wavelengths had all been stretched or shifted to the red end of the spectrum. That is, all the wavelengths are more red than expected. Okay, so if you remember from the diagram that we studied last class, we studied this diagram, that the hydrogen absorption spectra. We are supposed to find the wavelengths here at lambda naught or lambda 0. We're supposed to find the wavelengths here because this is the expected wavelength and this is the actual wavelength released by the star. But by the time the light wave gets to us here, by the time we observe, the wavelength gets a little bit shifted, and it gets a little bit shifted to the red end of the spectrum. So it's a red shift. We call it a red shift. And we studied that in redshift means Doppler effect means moving away. So naming this effect redshift, Hubble realized that it must be caused by the galaxies all moving away from us at great speed. So this redshift made Hubble conclude that, okay, since light from all galaxies are redshifted, that means definitely all the galaxies are moving away from us at a very high speed, at great speed, because the light is not just a little bit shifted, it's a lot shifted. It's pretty much, it's a high value. The shift is a high value. So we will learn the calculation today. So from that calculation, we can Hubble concluded that the galaxies are all moving away from us and at very high speed. So this we did not study from the reading material, but rather I discussed from the slide. But it's the same thing. Let me read it for you. He realized that at the increase in wavelength. So, like I said, redshift is an increase in wavelength, right? Was the result of which effect? Do you guys remember? It's the Doppler effect. That's right. It's the Doppler effect. So, and then here on Earth, it is most commonly observed with sound waves, right? We studied this. I'm not gonna repeat the weird sounds. So in Earth, it is mostly observed. The Doppler shift effect is observed. Sorry, is heard rather for sound waves emitted by fast-moving objects such as car or train. Right? When a car moves in front of you, oh well, I'll just say it again. Meow. Right? So like it's high frequency and then low frequency. It's high frequency when it is approaching you, and it is low frequency when it is moving away from you. Correct? So so according to Doppler shift, if as the source of the wave approaches, the frequency seems to be higher than actual, and as the source of the wave moves away, the frequency seems to be lower than actual. All right. Now, if this is described in details here, If the moving object sounds its horn as it passes us, then the sound waves we receive appear to have a shorter wavelength and higher frequency as it approaches. So this is very very important. Shorter wavelength and higher frequency as it approaches, like very high pitch, right? And a longer wavelength or lower, or rather this should be and. Let me just correct it even. This should be and, okay? Like not or, this should be and. Okay? Oh, well, what the hell? Okay, so this should be and. So and a longer wavelength and longer wavelength, sorry, longer wavelength and lower frequency when as it moves away. So this is very very important. This is the Doppler shift, the Doppler effect summed up in one sentence. Okay, when it approaches this, it gives a shorter wavelength and higher frequency. When it moves away, it gives a longer wavelength and lower frequency. In the case of sound waves, this means that they would have a higher frequency and pitch as the vehicle approached and a lower frequency or pitch as it moved away, right? But what would it mean in the case of light waves? Well, since all the galaxies which he observed, Hubble, by he they mean Hubble, which he observed appeared to be moving away from us, so all the galaxies are moving away from us, with the more distant galaxies moving fastest of all. Okay, so the more distant galaxies, that is the galaxies that are far away from us. This is very very important, by the way. Let me more distant galaxies moving fastest of all. How do I explain this? Um, it's like think about like a galaxy that is very close to us. For example, a galaxy in our local group. That galaxy is moving away from us, but not at a very high speed. A galaxy that is farther away has an even higher speed of moving away, and a galaxy that is even farther away is moving away even faster. So this is very interesting. Like the farther the galaxy is, the faster it is getting even more further. Get it? Like the farther a galaxy is, the faster it is moving away from us. Okay, so the more far apart you get, the faster you get away from each other. Okay, so it's even a thought of philosophy. The farther you get, the faster you like forget each other or move away from each other. Anyway, so the farther the galaxy is, the faster it is moving away. The point of giving all those examples is that you need to remember this very well. This is very important information. This was Hubble's main observation. Like people had kind of observed that the galaxies are moving away, but Hubble was the first one who observed that the farther a galaxy is, the faster it is moving away from us. And this definitely proves the balloon expansion theory that we studied, kind of. Remember the balloon, expanding balloon? So this made Hubble realize that these observations meant that the universe was expanding. So question to you. What were the observations of Hubble that made him think that the universe was expanding? Think about it a little bit. What was the observations made by Hubble that made him realize that the universe was expanding? Well, first of all, Edwin Hubble made observations of very distant galaxies, all of them well outside the local group. And then what did he do? By splitting the light into its spectrum, because otherwise you cannot tell what's the wavelength of the light. So you first need to split the light into spectrum. So what did Hubble do? By splitting the light into its spectrum, he observed redshift, which meant the galaxies are all moving away from us. And then, which he realized because increase in wavelength by according to Doppler effect meant like moving away. Okay. Then he observed that like he compared the distance of the galaxies to their speed of moving away. And by comparing that, he saw that the more distant the galaxy, the faster it is moving away. These observations made Hubble realize that the universe was indeed expanding. Okay? And Hubble was able to use the Doppler effect equation, the equation that we learned last class, to calculate exactly how quickly each galaxy was moving away from us, as illustrated in the following example. Okay, so Hubble, since he had the Doppler effect equation, he could exactly calculate how quickly a galaxy is moving away from us. Okay, so like we know from redshift you can tell that the galaxy is moving away, but from a calculation you can tell how fast the galaxy is moving away. I hope that is clear. If that is clear, before we get to the example, I want to just write down the points that I mentioned here. So what are the points that I just mentioned here? This the redshift shows that okay, I'll get to that a little bit. First, let's get into here. Let me just. Oh, okay, sorry. Yeah. So, what are the points that we just studied? We just studied that Hubble made observations of very distant galaxies by splitting their light into spectrum. He observed that light from all galaxies are redshifted, which means increase in wavelength. So all galaxies are moving away from us. Also, the more distant a galaxy, the faster it is moving away. These observations concluded that the universe is expanding. Clear? So these are the observations that make us conclude that the universe is indeed expanding, no doubt about it. Clear? Any questions so far? I will continue after this. After I'll give a prayer break right now, and I'll continue after that. Okay? Ah, good. Cool. All right, cool. So let's just take a prayer break. Uh, let's make it 7 minutes, okay? 7 to 10 minutes actually, yeah, about 10. So yeah. So I'll see you in 7 minutes. Thank you. Back. <clears throat> Okay, we are back online. Yes. So, what was the point? 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 Yes. So, what was the It took much longer than 7 minutes actually. I underestimated the time taken. Okay. Nah, 6:45 na? 6:40 was it? Alright, anyway. Can we resume? Yes, let's resume now. Uh, okay, let's resume with this example question. The different colors or wavelengths within the light from a distant galaxy are separated. By separated, you understand what it means? By separated, they are saying that it has been. Oh, you can see that. Oh, right. So by separated, it means that it has been split into its spectrum. Okay, good one, Ravin. Oh, okay. I'll wait a little bit more. 8 watching. No, we're. I think it's all right. Let's continue. So, like I was saying, the different colors or wavelengths within the light from a distant galaxy are separated. That is, the different colors or wavelengths from the light within the light has been split into its spectrum. So a wavelength of 6 into 10 to the power minus 7 meter is received on Earth at a wavelength of 6.3 into 10 to the power minus 7 meter. So a wavelength of this, okay, is received on Earth at a wavelength of this. Alright, now try to understand. 6 into 10 to the power minus 7 meter. This is the actual wavelength, but it is received on Earth at a higher wavelength of 6.3 into 10 to the power minus 7. So there is a increase in wavelength or redshift going on here. So use this information to calculate the speed at which the galaxy is moving away from the Earth. So bole dise moving away, even if it was not stated that it is moving away, we could guess. Even if this was not given, we could still guess because it is an increase in wavelength. So it must be moving away. Okay, so calculate the speed of the galaxy. So what's the formula? This is our formula, right? Del lambda by lambda is equal to V by C. What is delta lambda? The change in wavelength. So this is the new wavelength minus this is the original wavelength. This is the actual wavelength that we receive. This is the wavelength that we receive, and this is the actual wavelength. So actual wavelength is the reference wavelength, that is lambda 0. So this is lambda 0 because this is the actual wavelength, and 6.3 into 10 to the power minus 7, this is the wavelength that we receive. This is the lambda. Okay, so this is lambda, the wavelength that we receive, and this is lambda 0, the wavelength, the original wavelength. Okay, the reference wavelength. So the difference between these two, that is 6.3 into 10 to the minus 7 minus 6 into 10 to the minus 7, this will be the delta lambda divided by lambda. Which lambda? This should be lambda 0. They missed a 0 here. This should be lambda 0. So this should be 6 into 10 to the minus 7. So using the formula, what we can get is, okay, they didn't really write it in a. I'll write it in a way that you understand better. Okay, let me just write it here. So this formula we know that delta lambda by lambda naught, lambda minus lambda naught divided by lambda naught is equal to V by C, right? So let's just do it here. Okay, so we know this equation, fine. Uh, so we know this equation, right? Now we can go to next line. If we go to next line on this, and we insert another equation, that will be another fraction equal to another fraction. So what will be here? Delta lambda, that is lambda minus lambda 0. So lambda was what? 6.3 into 10 to the power, so 6.3 times 10 power, there should be power somewhere, yeah. Oh no, oh damn it. Okay, let me just, okay, seriously, okay. Oh wow, sorry about that. Yeah, cool. Okay, not cool. I just want this. Oh, okay, let's go. Yeah, sorry. Technical errors. Okay, so 10 to the power minus 3, minus 7, right? Minus, and then it will be what? Actually, it will be far better if I just directly do it on the calculator. You can watch me do that. That's far better, actually. Yeah. Let's just do it on the calculator, yes, because that's just far better. Oh wow. Okay. Okay. Even the calculator is not working right now. Never mind. Let's continue. Sorry, so many technical errors today. Okay. So 6. I hope you guys don't mind. Seriously, I'm sorry. Yeah. Okay. So you can do this math probably on your own, but I'm still showing it anyway because it's the first time that we're doing it. So divided by will be lambda 0. So lambda 0 is the original wavelength. That will be 6. That will be 6 times. Where is times? There is times. Uh, 10 to the power minus 7. Yeah, that was long time consuming. Is equal to, this will be what? Your speed of the galaxy. This is v that I don't know. I need to calculate this. Divided by c. What is c? Speed of light. I know this. So 3 into 10 to the power 8. So let's just do it that way. 3 into 10 to the power 8. Whew, phew. So you can calculate v from here, right? And that will be the speed of the galaxy. If you calculate v from here, it will be, damn it, small v. Yeah, v from here, the answer will be 1.5 in 10 to the power 7. Another 10 to the power. Great. 1.5 into 10 to the power 7. Not 87, 7. Meters per second. Meters per second. Yeah. Okay. So you understand the math? Does anyone have any questions? This is the answer, and let me just show the question again. Oh, you guys are seeing the question now. So far, any questions in this class? Today's class. In total, I will look at all of your questions so far now. So, prism, using prisms, using not using prism. Okay. Redshifter, meow. Oh, okay. Is there a like off topic later? Redshift equal to increase in, no. Redshift is equal to increase in wavelength. Redshift is increase in wavelength, decrease in frequency. Conduct philosophy classes. I would actually love to take philosophy classes. Like, I don't know philosophy much, but like, I've read a little bit. I've read some books, yeah. So why though learn philosophy? Hubble, not Hubble. Why do more distant galaxies move faster? As balloons expand more and more, we can see a white mark on the material. Can that too happen to universe? No, no, no. Um, okay, so what is dark matter and ordinary matter? I'll get to that. I'll get to that later. Very good question. Keep that in mind. And finally, the expansion of the universe is the increase in distance between any two given gravitationally unbound parts. What are those unbound parts? Between any two gravitationally unbound parts. No part, nothing is to be to be strictly speaking, nothing is gravitationally unbound. However, for example, if you go enough far away from the earth, then the gravitational attraction of earth and you, the gravitational force of attraction between earth and you, if you go very very far away from earth, then the gravitational force of attraction between earth and you will be so small that it will be almost zero. So then we can say that you and the earth are now gravitationally unbound. Okay, technical error. Okay, redshift equal to increase in wavelength and decrease in frequency. Yes. Positive electron. What? Top galaxies are almost. I'm not gonna answer that right now because like I cannot speak for all galaxies, but for those galaxies that I have studied, and as far as I know, most galaxies, yes, most galaxies have have a black hole at their center, or they can have multiple black holes even. Okay, it doesn't have to be one black hole. Okay, so moving on. This math we get it. So an alternative way of approaching calculations like this is to use the fact that percentage shift equal to percentage of speed of light. I will skip this, but if you want to, you can read this. I will skip this part because I don't want to calculate this way. I prefer the. I think you guys will also prefer the above way. Delta lambda by lambda naught is equal to v by c. The formula in the slide. I prefer that method, so I'm not going to talk about this method. This alternative method will not be very useful actually. Um, Although they are saying can be useful for checking. Okay, so it can be useful for checking, but you're going to do the actual calculation in the above using the above formula. Okay, now let's talk about this paragraph. Although at first glance, the fact that every galaxy outside our local group is moving away from us might suggest that we are at the center of the universe. This is not the case. Okay, so I talked about this, right? We are not at the center of the universe, but it seems like it. A better way of visualizing the situation is to imagine all the galaxies in the universe as dots marked on the surface of a balloon. So this is a recap from last class. You remember this balloon diagram. Okay, now the key idea is that it is the space between the galaxies, the rubber of the balloon, which is getting bigger. In one sense, the galaxies themselves are not moving around the universe, okay? They would be in exactly the same place on the balloon if it was let down again. So if the space between the galaxies decreased again, they will again be at their same position. So they did not move. It's just the space between the galaxies increased. This also explains why more distant galaxies seem to be moving away from us more quickly, because there is more space between us and a distant galaxy, so more space to expand. Okay, this is a book reference. You don't need to look that up. Like that would be way too much of a deep, uh, bigger dive into astrophysics. But we'll skip that for now. But you can if you want to, but I wouldn't recommend. Anyway, so what we're talking about here is basically that the farther 2 points are, if 2 points are this and this, they now that they are far apart, now there is more space between them that can expand, right? Before, there earlier there was less space between them that can expand. Now there is more space between them that can expand. So the more space expands more, and so the galaxies that are farther from away from us, they are moving away from us even faster and faster. I hope that makes sense now. Now, Now we are gonna talk some philosophy too. So, I love this part. Okay, so Big Bang or steady state. Hubble's discovery. Oh, okay. Before we get to that, any questions so far? Any questions? No. Currently in a pinwheel distance expanded is key admin in geometry. The expansion is accelerating, so you can say it's kind of like geometry. It's not exactly geometric series or arithmetic series. It's an accelerating expansion. I'll get to that. Very good question. Okay, Big Bang or steady state. Hubble's discovery that we live in an expanding universe. So this part is solid, okay? So this part is confirmed, no doubt about it. We live in an expanding universe. That's just fact. That's just true. You can look up at the sky, look at the light from any galaxy, you will see that the light is redshifted, which definitely means the galaxies are moving away, and the farther away a galaxy is, the faster it is moving away from us. So the universe is expanding, no doubt about it. Clear? Okay, absolutely no doubt about it. Great. Now, let's get into it. This led to the development of two competing theories. Okay, so this is interesting. Two competing theories. So, the steady state theory and the Big Bang theory. Okay, so this is, I will get a little bit technical here. When we say competing, we should not say theory, we should rather say hypothesis, okay, or speculation, or attempt at an explanation, okay. So from the expanding universe there, but for the sake of it, let's just simplify it and call it theories, okay. So the steady state and the Big Bang theory. So there are two theories now, the steady state theory and the Big Bang theory. Now, whichever theory, understand how physics works, okay, understand how the scientific community works in general. If you have two competing theories, there are going to be tests, and whichever theory can predict the future better and can explain the past better, that theory we will say works better, and we will keep that theory as the actual law and actual theory. So we will keep calling that one a theory, and the other one that fails to explain or that fails to predict, we will call that a wrong hypothesis, okay, or not wrong, at least wrong to certain extents, okay, so partly wrong. Now, what does the steady state theory say? Let's get into it. The steady state theory, developed by the cosmologist Fred Hoyle, proposed that the universe had always existed in a similar way it appears nowadays. So that's interesting. He's saying that the universe existed as it is forever. The universe has always existed. Yes, the earth came along, like the everything that we studied, like the sun formed from a nebula, from that earth formed, and then the sun is going to turn into a red giant, the earth is going to get gobbled up into the sun, and so on. All of that is correct, but the steady state theory says as long as we are talking about the universe, or like the total space, that has remained existed in a similar state, okay. So maybe some star is dying, some star is forming, but overall a similar state, okay. Although stars and galaxies are born, evolve, and die, so stars are born, they evolve. By evolve, we mean like they go from protostar to main sequence star to red giants, red supergiant, supernova, or white dwarf, or black hole, neutron star, etc. So they born, birth of a star. We talked about this, nebula to main sequence. They evolve. We also talked about this, either main sequence to red giant or main sequence to red supergiant. And die. We also talked about this, either die by turning into a white dwarf, or die by becoming a supernova and eventually a black hole or neutron star. Okay. Now, So many stars and galaxies are being born, they are evolving and dying. However, so like there's an although the evolve and die, the average numbers of each has always remained the same. Okay, that's an interesting theory. The steady state theory is saying the universe has always existed as it is, in a similar state to the way it appears nowadays. And so it says like stars and galaxies are born, evolve, and die. But if you take the average numbers of each has always remained the same. Okay, the average numbers of galaxies in our universe is the same no matter which direction we look from the Earth, and the state theory was suggesting that this symmetry extended time itself, implying that the universe had no beginning and would have no end. So the steady state theory is trying to say, look, if you look to the left from the Earth, you can see a number of galaxies. If you look to the right from the Earth, you can see a number. You look north, south, east, west, whichever direction, whichever direction we look from the Earth, whichever direction we look from the Earth, we look from the Earth, the average number of galaxies in our universe is the same. Okay, so he's saying the steady state theory given by Fred Hoyle. So Hoyle is saying, look, whichever direction you look, the average number of galaxies is the same. So it only makes sense that the average number of galaxies is the same. That means it has always been like this. It has always been same. So, or you can say, or he rather said, this is a symmetry. He called this a symmetry. Okay. So like mathematicians and theorists, they love symmetry. Okay, they just love symmetry. Symmetry is beautiful. We all love symmetry actually. Like uh, we always like we tend to like symmetric pictures. We tend to like symmetric objects. That's just how our mind works. And well, the galaxies seem to be symmetric because whichever direction we look, the average number of galaxies is the same. So Hoyle said maybe this symmetry extended to time itself. Like maybe time is also symmetric. If space around us is symmetric, then time is also symmetric. Like somehow implying that our universe had no beginning and would have no end. Okay, so the steady state theory kind of said that our universe would have had no beginning and would have no end. Okay, so that's the steady state theory. However, it's gonna fail, so we're not gonna focus on it that much. Let's focus on the one that can actually predict most of what we know. The Big Bang Theory proposed that. Understand the keyword here. Proposed that. So like it's still a hypothesis. It is being said. It is being like the Big Bang Theory is proposing that like it's a postulate that it's not a postulate but yeah it's a proposal. That's the perfect word for it. It's a proposal. So like the Big Bang Theory proposed that around 13.8 billion years ago our universe existed in an incredibly tiny space. Okay, so 13.8 billion years ago our universe existed in a very incredibly tiny space. And then what happened? It then began to expand very quickly, an event known as the Big Bang. And we can still see this expansion taking place today. This is perfectly correct. I wonder if I can make this more pop out. Can I change the... Let me just do this. Okay. Uh, never mind. Yeah. Okay. That was a waste of time. So, and we can still see this expansion taking place today. So, focus here. Okay. Just focus here, guys. Oh, okay. I can do that. Yeah. So That's now it's in more focus. Yeah. So we can still see the expansion taking place today. So this part is perfectly correct. We can see that the universe is still expanding, and we know that 13.8 billion years ago we are like proposing that. So this is a prediction about the past. Let's see if it works out. Although gravity has brought matter into together to create stars and galaxies in certain areas. So in certain areas, stars and galaxies is formed due to gravity. However, the space between the stars and galaxies are still expanding. So through the 1950s, so 1950s, not today, 1950s, there was a fierce debate. So there is no debate now. There was a debate in 1950s. All right. So through the 1950s, there was a fierce debate amongst cosmologists. Okay, so cosmologists are in like debate as to which of these two theories was the better explanation for the expanding universe. Okay, so which is the better explanation? And then, however, during the 1950s and 60s, there were two major discoveries which which tipped the balance firmly in favor of the Big Bang theory. So there were two major discoveries during the 1950s and 1960s, and these two discoveries tipped the balance. Basically, tipped the balance means settled it once and for all, like last nail in the coffin. All right, like settled it once and for all that Big Bang theory it is. So two major discoveries. What are these two major discoveries? The first one is cosmic microwave background radiation, and the second one is actually redshift. But they didn't talk about it. Okay, let's study them one by one. Let's see. So the first one is cosmic microwave background radiation. So this was in 1965. Two radio astronomers. So two radio astronomers, Arno Penzias and Robert Wilson, they detected a mysterious background of radio waves with a wavelength of around 1 millimeter. Okay, now we actually call them microwaves because this wavelength is much shorter than the common radio waves, so we call them microwaves. This is also the same wavelength that is used in your microwave oven, by the way. Just say. So so this wave, they just observe. They are radio astronomers, right? They are looking for radio signals. All right. However, they detected a mysterious background of radio waves with a wavelength of around 1 millimeter, which appeared, now this is very interesting, which appeared to be coming with equal strength. So, appeared to be coming with equal strength from every direction in the universe. So, from every direction in the universe, like look at this picture, it's spherical, right? From every direction in the universe, you are getting equal strength of radio waves. This picture just visualizes those waves. Okay, this picture is a visualization of those waves, and so you can see that the density of the dots is basically uniformly spread out. It's somewhere red and somewhere blue, but like somewhere high wavelength and somewhere low wavelength, but it's from equal strength, like slightly high and slightly low. The wavelength difference is very small. So from all directions, from every direction in the universe, it was equal strength. This cosmic microwave background radiation was quickly suggested. This cosmic microwave background radiation was quickly suggested to be left over from the Big Bang itself. So this radiation is called to be the leftover cosmic microwave background radiation. It's called to be leftover from the Big Bang itself. Let's read what's written in 12. Sometimes rather misleadingly called the echo of the Big Bang, but it's not actually the echo of the Big Bang. It's not an echo. It's actually a leftover, like a remnant from the Big Bang itself. Okay, the strength and wavelength of the CMBR, the strength and let me show this again. The strength and wavelength of the cosmic microwave background radiation (CMBR) was also shown to be consistent with a Big Bang which took place 13.8 billion years ago. Okay, so you are getting, so let me make help you make some sense out of this. Okay, before we get to this, actually no, let me continue to quasi-stellar objects, and then we can get to the explanations. Okay. Yeah, this image shows the tiny variations in the intensity of the cosmic microwave background radiation as measured by the in 2013. The tiny variations were a product of the fluctuations took place to the close to the very beginning of the universe. Okay. Now, what are quasi-stellar objects? In the late 1950s, again late 1950s, as the power of telescopes increased, so a number of extremely compact objects with very large luminosities. So these are very bright but very compact. So very small, very compact but very bright were discovered. They all had exceptionally high redshifts. Alright, suggesting that they were at enormous distances, because we know that the farther a galaxy is, the faster it is moving away. So the more its redshift will be. Now, since these compact objects with very large luminosities have exceptionally high redshift, since these have very high redshifts, so they must be very far away. So they are at very enormous distances from the Earth and receding at, like, moving away. Receding just means moving away. Moving away. All right. So receding from us. Yeah. So receding at speeds close to the speed of light. So, like, we just saw that we can calculate the speed of at the speed at which a galaxy is moving away from us from the redshift. Well, when the astronomers calculated the speed of these extremely large luminous objects, very large luminosity, very compact objects with exceptionally high redshifts at enormous distances, their speeds turned out to be very close to the speed of light. So these are moving away at very fast speeds, almost close to the speed of light. Their exact nature was not clear, like what they were, that was not clear, and so they were called quasi-stellar objects, or they were just named quasi-stellar objects, QSOs, or quasi-stellar objects. So they were named this because their nature was not clear, but like they are stellar objects, obviously they are like the stars, but they are very far away, and they seem stationary to us because they are very far away. So they were called quasi-stellar objects, but they were very, very bright and moving away from us at very high speeds. Quasars. This Hubble Space Telescope image, this is a telescope image from Hubble Space Telescope, shows QS this. A massive black hole at the center of a galaxy. Even though it is one of the most distant objects visible from Earth, it still appears to shine brightly, indicating the tremendous power output of the quasar. Okay, so this is actually around a black hole. All right, so the QSOs are now known to be the nuclei of galaxies, or active galactic nuclei, AGN. The QSOs are now called AGNs, that is active galactic nuclei. It's like the nuclei of galaxy where there is a black hole and all the stars of that galaxy are collapsing there and colliding there, and like huge energy, huge power is being produced. So they shine very, very brightly. The importance of QSOs for the debate between the Big Bang and steady state theories of the universe is that they are only found at very great distances from Earth, almost at the edge of the observable universe, like almost at the edge of the last thing that we can see. Whenever astrophysicists look out across great distances in space, understand this. Whenever astrophysicists look out across great distances in space, they are effectively looking back in time. Okay, let me explain this a little bit more. Why? In the next line. Yeah. For example, when looking at a galaxy at a distance of 5 million light years, so a galaxy is at a distance of 5 million light years. Okay, a galaxy is at a distance of 5 million light years. This means how long does light take to travel from that galaxy to Earth? It takes 5 million years. That is why the distance is called 5 million light years. That is, it's gonna take light 5 million years to reach Earth from that galaxy. It's like if a star is 5 light years away, then light will take 5 years to come to Earth from that galaxy. If a galaxy is 5 million light years away, so light will take 5 million years to travel to Earth from that galaxy. So astrophysicists are seeing it as it appeared 5 million years ago. So whatever light we are seeing, that light is from 5 million years ago, right? So the state that we are seeing, that it is very bright, it was very bright 5 million years ago. We don't know what's happening to it now. The light that we see, very bright object, that very bright light is coming from 5 million years ago. Okay, since its light will have taken 5 million years to reach the Earth. Now understand this. The nearest quasar, that is quasi-stellar object, or like galactic nuclei, or like very bright objects, the nearest quasar is at a distance of 1.5 billion light years. 1.5 billion light years. So even the nearest quasar. So definitely that quasar was, so like, which means that they only existed up until 1.5 billion years ago. So whatever we are seeing, the bright light, that existed 1.5 billion years ago. This means that the steady state theory's idea that the universe has always looked broadly the same cannot be true, because this is how it looks 1.5 billion years ago. That means maybe our Earth also looked like this 1.5 billion years ago. Right? Because if that galaxy far away from us, that looks like this 1.5 billion years ago, that means our galaxy must also have been looking like that 1.5 billion years ago. So it cannot be that our galaxy has always looked the same way that it looks right now. Correct? Because right now we are seeing it as like a steady galaxy, but 1.5 billion years ago we don't know. But if we see another galaxy 1.5 billion years ago, we see that it is a very bright ball, right? Consequently, the Big Bang theory is now the dominant theory in cosmology. Now I'm gonna explain a little bit more, like how Big Bang theory can explain the quasar. Okay, how Big Bang theory can explain this very bright source of light. Why everything at one point very bright? The Big Bang theory can actually explain that. Well, I'm gonna talk about it. So let's get back to the slide. But before that, of course, you will have a lot of questions. I assume you have a lot of questions probably. So I will answer some of your questions, so and then I'll get to this. Yes, the steady state theory has been proven wrong actually. Like I said, 1950, 1960s. Yes, it failed because the universe is expanding, so the density is decreasing. The density, like I said in last class, the space is increasing, but we cannot be sure about the density because stars are constantly forming and then again dying. And once a star dies, it once a star for example, when a star burns hydrogen, mass is like no, not really, but like when energy travels really fast, it gets converted to mass. All right, so mass can change of the universe. So we cannot be so sure about the density. Are the matter ordinary or dark matter? There are both ordinary matter and dark matter. Is dark energy greater than gravity? Yes. That is why the universe is expanding, because otherwise it will collapse under gravity. না চা খাওয়ার ব্রেক দিব না. Space theory. Why Big Bang theory is called the Big Bang theory? Was there an explosion? No, there wasn't an explosion, but there was a very rapid expansion that we can call kind of like an explosion, but it wasn't an explosion actually. So from that can we track the place of Big Bang? Why is there a CMBR? Then why is there a CMBR? I'll get to it. Like this is why there is a CMBR. Yeah, this is why there is CMBR. As I was saying, we don't hear CMBR from normal explosion. So why does the Big Bang? No, we don't hear CMBR. We see CMBR. Okay, so like it's a microwave. We can like sense it using our sensors. Okay, and it's not an explosion. The Big Bang was not an explosion. It was an expansion. There's a difference. I'll explain further in a little bit. If they're looking forward, are they seeing the future? No, they're seeing the past, not the future, because light takes time to travel from a distance. Even when you are looking at the clock, even when you are looking at the clock, you are actually seeing time very slightly um, past. Because let's say you look at a clock that is far away, a clock that is on the sun. It takes 6 minutes for light to come from the sun to earth. 6 minutes. So if you look at a clock on the sun, that clock will always be 6 minutes slower. So you're looking at light from the sun. The light that we see from the sun is actually 6 minutes past. So we are always whenever we are looking at an object that is far away from us, it's we are looking at past. This is why we can find aliens. Kind of yes, like if aliens exist. So like this is where the that's a very good observation. Like you can read up the Fermi paradox on this topic. My head hurts. Okay, I'll end it here and explain this CMBR and more this diagram in more details in the next class. I'll end it here today. Any more? I'll end it with your questions today. In next class, I will re-explain CMBR and the quasars. I will re-explain that topic in the next class. I'll end it here today. Any more questions? Fermi paradox. Yes, read up on it. Fermi paradox. If you want, knock me on Messenger. I will give you a very good link to it. There's a very good article written by Tim Urban in Wait But Why about Fermi paradox. You can read that. Okay, so you guys are tired, and also this is a lot to take in. So I will explain the cosmic microwave background radiation and redshift and quasars once more with this diagram, and also I will explain it by from actually I just received an email from Professor Don Lincoln. He's an amazing guy, Professor Don Lincoln. He is an astrophysicist who works at the Fermi Lab, and he has a YouTube channel called the Fermi Lab. You guys can check out that YouTube channel. And I asked for his permission to use his one of his video in my live stream class, and I will use it in the next class to explain this phenomena. And this picture is actually from that YouTube video, so don't miss next class. Okay? That's it for today. Thank you. Allah Hafiz. See you next class.